Today, lesson 52b, a deeper look at linear relationships. That has been our focus as of late. Some proportional, some linear relationships not proportional. In addition to that, yesterday, our focus was extending the one quadrant idea into 4 quadrants. And so here is a little bit of background knowledge. This is not the one that's in your notes, but what we've been working on is filling in tables when x is 0. Remember, we're simply substituting 0 in here for x. 3 times 0 is 0, and 0 plus 2 is 2. And then we continue substituting 1 in for x, substituting 2 in for x, and so on. And we get these values. And we plot them. Draw our line through. And this is clearly, as you look at the equation, was not a proportional relationship. And the graph confirms that it is not. And the unit rate for this one is, there's an increase of 3y for every 1x, and that is our unit rate, all the way up the ladder there. And the initial value is when x is 0, y is 2. It can be found in the table, it can be found on the graph as well. Well, today we're going to add the 8th grade terminology for unit rates, and that is slope. So today, I won't be calling it unit rate anymore. I'll be calling it slope. And the 8th grade word for initial value is actually y-intercept. So I don't know if you want to add something somewhere in your notes, but from here on out, and I may still ask unit rate, but what I want you to understand is that these two ideas are referring to the same idea, the same thing. Same thing here, initial value is referring to the same thing as y-intercept. Okay, and I will define both of those things in just a second. So here's the graph that's in your notes. That is the graph of y equals 2x minus 3. We define the slope of a line to be this. It is the vertical change over the horizontal change. And here's where you start filling in things in your notes. Now notice how I used in red the letter m there. We typically, instead of writing slope equals every single time, we typically use the variable m to represent slope. Now this idea of vertical change over the horizontal change, look, this is what I've been showing you, I think, for the last 4 lessons now. I've been showing you we are increasing positive 2y in the up vertically, right? And we are horizontally having a change of positive 1x. I've been showing you that all along. Vertical change over the horizontal change. But typically, there's a shorter way of saying that, and you've probably even heard this before. Sometimes slope is referred to as rise over run. And that's kind of how we will talk about it. Rise meaning vertical change, and we can't have negative vertical change, negative rise, and we can't have negative horizontal change or negative run, so we just have to pay attention to what we're doing. So slope is referred to as rise over run. So let's use this graph here to define all of those things. So we know that slope is rise over run. So on our graph, and I already kind of showed you that, to get from one ordered pair to another, and I usually will start at the y-intercept or the initial value, we're rising 2 and we are running positive 1. If we simplify that, that of course is 2 for our slope. It's also the unit rate, or the numeric value of the unit rate. I guess I should be a little more specific there. Now, you do not have, and this is where you really need to be paying attention here, you do not have to start at the initial value. You can start from any ordered pair and work your way to the next ordered pair or another ordered pair. So watch. I'm going to start from that ordered pair, and I am going to rise negative 4. I'm going down 4. That's negative 4. And then to get to the ordered pair that's in line with it, I'm going to run 2 to the left, which is a movement of negative 2. Well, we rise negative 4 and we run negative 2. If we think about that, that still is 2. So it does not matter where you start and where you finish, as long as you're starting on one ordered pair and working your way to another one. You will always get a numeric value of a unit rate of 2 or a slope of positive 2 in this case. Now the other important piece in this graph is the y-intercept. And we've got more stuff to fill in this problem. The y-intercept of a line is defined to be the point where the line crosses the y-axis. Make sure you fill that in, please. So if we take a look closely at this graph, the y-intercept is right there at -3. That's where the graph crosses, or the line crosses, the y-axis, right there at -3. Now we've been laying this out in the last 2 lessons. That the unit rate, the numeric value of that, is very important, and the initial value is very important. Now we're referring to that as the slope and the y-intercept. So if you look right here, we call this the slope-intercept form of the line. Can you write that in? Slope-intercept form. It's called slope-intercept because right there is the slope. And right here, with the sign in front of it, that is the y-intercept, and we typically use the letter B to represent the y-intercept. M is typically the variable to represent slope. B is typically the variable to represent y-intercept. So if we know those two things, we can quickly find the equation of a line. Before we even get to that, let's do a little bit of practice of finding slope. And one more time, the slope is the numeric value of the unit rates, and the initial value is essentially the y-intercept. Okay. Number 1, find the slope. So in order to do that, like we've done the last 2 or 3 days, you're going to have to find some perfect ordered pairs first. Go ahead and do that. Once again, find some perfect ordered pairs. Use dots to represent that. And then use this new idea of finding the slope. First thing we need to do is find some perfect ordered pairs. I see one right there at -2, -2. I see another one right there at 1, -1. And I see another one there at, 4, 0. Doesn't matter where you start or where you finish. You're just trying to get from one ordered pair to another. So I'm going to do it this way first. I'm going to rise 1 to get in line with the next ordered pair. And I'm going to run 3 in the positive x direction. The slope is defined to be the rise over the run. I had a rise of 1. I had a run of 3. So that means the slope is positive 1/3. Could you have done other things? Of course you could have. You could also have gone, let's see here. You could have gone from here. So that would be a rise of -2. And backwards this way, that would be a run of -6. And -2 over -6 is still 1/3. So it doesn't matter where you start or where you finish. You're just trying to get from one ordered pair to another. Now, we're going to prove this by using an idea of similar triangles, where we're trying to create triangles that are similar to each other, where one is a reduced version of the other or one is a blown up version of the other. So let's take and do this. Let's kind of shade it in to create a triangle there. And we're really creating a right triangle there with a rise of 1 and a run of 3. And so when I say proving with similar triangles, you're going to have to prove it with 2 or 3 maybe similar triangles. So I'm going to create another one right here. That one has a rise of 2 and a run of 6. And of course, 2 over 6 is 1/3 as well. So make sure if you're asked to prove with similar triangles, really all you're doing is you're shading in your rise over run area. That's really all you're doing there. Okay? And proving to me that you're going to come up with the same exact thing. All right, everybody try number 2. Find the slope below with at least two similar triangles. Lots of things you could do here, but no matter what, the first thing we've got to start with is finding some perfect ordered pairs. I found those three right there. And one way that I did this is I started from that one and went over to the other one. So I'm rising 3 and running 2. So that means the slope is 3 over 2. Rise 3, run 2. And make sure you simplify it. So 3/2 is the slope for that similar triangle, or that triangle I should say. The next one I'm going to go from the bottom ordered pair up to the top one. So I have to rise 6 to get in line with that and run 4. But when I simplify that, I of course get 3/2 also. So using similar triangles, creating either reduced versions of your original one or blown up versions of your original one to prove that the slope really is what you claim it to be. Okay? All right, let's go to number 3. Number 3 is asking you to do it with 3 similar triangles. And then I've added one more question in number 3, and that is for you to find the y-intercept. So go ahead and do all of those parts. Number 3, here's what I did. I used 1 right there, using the y-intercept of -1 and going up to 1, 2. That gives me a rise of 3 and a run of 1, so we can clearly see the slope is 3, but we've got to prove it with 2 more. I'll do this one right here. Going from -2, -7 up to the y-intercept, so that's a rise of 6 and a run of 2, both in positive direction. That simplifies to 3. And then one more, I'll go with that big one right there. That one has a rise of -15, I think, because we're going down 15 from here down to here. We're dropping 15, and then we're going left 5, so that's a movement of -5. So I have a rise of -15 and a run of -5, and that gives me, once again, a slope of 3. So we can see the slope is 3. The other question I asked you is, what is the y-intercept? Well, of course, the y-intercept is right there at 0, -1 or -1. And so that is our y-intercept. And remember, we can use the letter B to represent the y-intercept. Okay. Now, how many more of these do I have for you to do? Okay, just on 4 and 5, you do not have to do it with similar, you don't have to do a bunch of similar triangles. Just find the slope and find the y-intercept. That's all I need you to do. So go ahead and do number 4 and number 5. Find the slope, find the y-intercept. Use the letter M to represent slope, use the letter B to represent y-intercept. Quickly. So in this one, slope is, I'm going to start at the y-intercept and go up to the next perfect ordered pair. So that's a rise of 2 and a run of -1. So that means my slope is -2. And I could have done it with multiple ordered pairs there. It does not really matter. I only asked you to do 1. Doesn't matter where. I'm still going to get a slope of -2. And we can clearly see the y-intercept is 1. So what's the equation of that line? Yes? Y equals -2x. Is that it?
Y equals -2x plus 1.
Yes. Now, I didn't ask that question, but that's really what it is. If you have the slope and the y-intercept, you're done. Y equals -2x plus 1 because the slope is -2 and the y-intercept is 1. Number 5, same idea. Slope, and this one will be -2/3 because we're rising 2, running -3, going from that order pair to the next one. I could use multiple order pairs to figure that out. If I did that one, or those 2 order pairs, excuse me, I would be rising 6 and running 9 to the left, so that's a movement of -9. But positive 6 over -9 is still -2/3. And I could even go this direction, which would be a rise of -10 because I'm dropping from here down to there is a movement of -10 of a rise, and to the right 15, that is a positive 15, but that simplifies to -2/3. And then my y-intercept is negative 4. So if I asked you what the equation is, you should say y equals negative 2/3 x minus 4. Okay? All right. Finding slopes from tables. Now, you have two choices here. One is I could make you plot all of those ordered pairs like this, and then do what we did in the last 5 problems. That would be pretty easy. However, that can be time consuming because you should be able to find the slope without that graph. So there are certain things we have to do. First of all, we have to make sure the ordered pairs form a line. Okay, we have to make sure of that. And on a graph, it would be easy to see. And then, from there, we use the definition of the slope of rise over run, and we could see that the slope is 3. But what if we did not want to graph? What if we did not want to graph? Well, we're going to use an idea that I hinted at yesterday, and that's by using ratios in tables. So what we're going to do is we're going to figure out, using this vertical change over horizontal change, or rise over run, or another way of phrasing it, change in y over the change in x within our table, and compare those ratios. So to go from 4 to 10, as far as the y numbers go, we have to add 6. And here's where you should be writing stuff down. To go from 1 to 3 with the corresponding x values, that would be a positive 2. So if we take that ratio of the changes in y over the changes in x, we get 3. Well, guess what? If we're going to prove that the slope is 3, we got to check all of them, because all of the ratios need to be equivalent, like in all the other table problems we've done. So if we do that, to go from 10 to negative 5, that's subtracting 15, or adding negative 15. To go from 3 to negative 2, we're subtracting 5, or adding negative 5. That ratio simplifies to 3. To go from negative 5 to negative 2, we are adding 3. To go from negative 2 to negative 1, we are adding 1. That ratio simplifies to 3. To go from negative 2 to 1, we're adding 3. To go from negative 1 to 0, we're adding 1. That ratio simplifies to 3 of the change in y over the change in x. And to go from 1 to 7, we are adding 6. And to go from 0 to 2, we're adding 2. That ratio also simplifies to 3. If all of the ratios of the change in y to the change in x are equivalent, that proves two things. It's linear, and whatever they simplify to, that is the slope. So the slope is clearly 3 in this one. Okay? Any questions with that idea? All right. Find the slope and the y-intercept in number 7. We need to compare the change in y over the change in x. So, here we go. I'm doing all the changes here. So we have negative 2 is the change in y from the first order pair to the second. The change in x is positive 4. That simplifies to negative 1/2. So at this point, we're just trying to see, do they all simplify to negative 1/2 as far as the change in y over the change in x? And it's certainly looking like they do so far. And we can see right now they do. So that means the slope is negative 1/2. Any questions on how I did that? The second question is, what is the y-intercept? And obviously that's right there at 0, negative 4. And so the y-intercept, and I don't know why it says 1 right there. I forgot to change it, obviously. This should say negative 4 right there, because of the ordered pair right there. I will have to fix that. All right, number 8. Now I'm asking for the unit rate. Now remember, the idea is the same. It's just that typically when we get to more of a real-world problem, and in a real-world problem, I'm comparing, number of candy bars to the cost rather than just x to y. So at that point, instead of asking for slope, I'm asking for unit rate. Same idea. Go ahead and try it. All right, Brooke, what's the unit rate?
75 cents per candy bar.
Thank you for answering it correctly. It is 75 cents per candy bar. The slope of a line is the same thing as its unit rate, so we're still finding change in y over change in x, and we simplify those ratios, and when I do, they all simplify to 0.75 or 3/4, and that is 75 cents per candy bar as far as the unit rate is concerned. Okay? By the way, what's the y-intercept? It's 0, because this is basically a proportional relationship. Okay? All right. Everybody do number 9, 10, and 11. Number 9, we're finding the unit rate because once again we have more of a real-life problem comparing time to distance. And the unit rate in that one is 34 miles per hour. Once again, by showing the change in y, or the change in distance to the change in time, 34 over 1 and so on, they all simplify to 34, so therefore it is 34 miles per hour. That is a proportional relationship, by the way. Number 10, we're asked to find the slope, and typically when it's just x and y, we refer to it as slope instead of unit rate. Finding all the change in y to the change in x, they all simplify to -6, so therefore the slope is -6. Then we come to number 11. And some of you did what I warned you about probably about 8 or 9 minutes ago. You have to check all of the ratios, because here's what I saw too many people do. They went, all right, well that simplifies to -1/2, and that simplifies to -1/2, and that simplifies to -1/2, comparing the ratios of the change in y to the change in x. Well, then the slope must be -1/2. Well, I have something to tell you. It's not. Because even though the first 3 simplify to -1/2, that one does not. Therefore, you can stop. That means this is not linear. So since the ratios of the change in y to change in x are not equivalent, this is not a linear relationship. In other words, if you plotted all of them, they would not all line up in a straight line. Most of them would, but one of them would not. Yes? What's that? You are right. It is +4. What is the other one's right though, right? This is +4. I mean, it still doesn't matter, right? I mean, it's still not linear. So this would be 4 here and -2/5 right there. So I'll need to fix that one as well. But it's clearly not a linear relationship. All right. So our last couple of problems today. In number 12, you are asked which situation has the larger slope. So you have to find the slope in both situations. Which one's larger, A or B? And then in number 13, you're doing the same thing and trying to figure out which one has the larger unit rate. So I'll give you about 2 minutes to do that, and then we are finished for today. In number 12, part A has a slope of 3. Checking the ratios of the change in y over the change in x. Looking at the graph for part B, that has a slope of 4. Rising 4, running +1. And so B has the larger slope. In number 13, checking the unit rate of part A, checking the changes of distance over the change in time, you get a unit rate of 6 miles per hour. Part B, you don't have to do anything. You're looking at the slope right there. 31 over 6, last time I checked, was 5 1/6. So therefore, A has the greater unit rate. Okay? Any questions? All right, we are finished for today.